We talked about normal distribution. Uh, the distribution is normal if it has this shape going up and then down, because normally that's how it happens. The middle region has highest frequency or highest probability to occur, and the end parts have lower probability. And so this shape of the curve is called bell-shaped because it has the shape of upside down bell. So that's the shape you need to look for if the question asks you whether it's a normal distribution or not. Then you need to see whether it's a bell-shaped curve or not. Now, the bell-shaped doesn't mean it has to be perfectly bell-shaped. So if the shape is writing on the board, the shape basically has to be going up and down. So it could be going up like that and then down like that, or it can be like this, kind of skewed. Still, it's normal. We'll be discussing those later when we go to the chapter on normal distribution. That's coming up later. This normal distribution is something we'll be studying a little more. All right, so let's go to basic statistics again. Organizing data. In statistics, if you're given, you'll be given basically a whole bunch of numbers, and they tell you what they are, and then you have to study, analyze them. So here I'm using an example to show you how to begin analyzing. First, you have to organize them into a frequency table, what we call. So you're gonna practice that using this example. So these numbers are given to you as grades of students in a class. So it's given in a random order, like, in the order that the instructor has. It's not in increasing order, decreasing order, none of that. So all you know is these are the grades. And the random variable X represents the grade of randomly selected student. So if I select a student randomly, what is the grade of that student? That's what the random variable represents. Then, now remember, in statistics, you have to define the random variable that represents what you're analyzing. Only then it's easy to analyze it mathematically. So this problem says if X represents the grade of the random student, then write the frequency table of X, and then write probability distribution of X in the same table, and then draw the histogram. All right, so you need to begin by introducing the title. Grade is our random value of the random variable. So random variable X represents grade. So you can write that if you like, grade of a random student. And the frequency goes here. And we use F to represent frequency. And we usually write FI, depending on some books will write FI to mean ith frequency. Also, here they will say the value xi. That means we are writing the frequency for each value of the random variable. So they may write x equal to xi or simply xi. It doesn't matter how you write the column title. But these are values of the random variable going in the first one, and frequencies of those values going in the second one. So let's do that first. You always start at the lowest value, which is 40 in this case, and then count how many times it's there. So when we actually do it, this is a short list, but in reality, if you're doing a statistics analysis problem, you will be given like 200, 300, or 2000 data. So you have a whole bunch of numbers here, and it's hard to work with it unless you do it in an organized way. So what you do is, as you count a number, you immediately cross it out using a pencil. So I'm going to just mark it red as I count it, but you need to, so realistically, when you're doing it, you will be crossing them out. So I'm counting the 40s and I'm crossing them out as I count. Okay, so there are 3 40s. So I write the frequency 3. And then you go to the next number, 50. All right. All right, I hope you're working with me. Let's write those numbers down. How many 50s are there?
4.
4.
4. Right. Okay, thank you. And how many 55s?
5.
5 is right. Okay, very good. 60?
5.
3,
Not 6.
5, 6. Right, 6 is right. Okay. There is no 65, so next one is 70. Okay, 70. 1, 2,
That's 6, I think.
3, 6. You're right. 6 70s are there. And there's no 75. 80 is next.
I think that's 4.
1, 2,
4.
3, 4. Right. Okay, very good. 4 of them. 90 is next.
3.
There's only 2. Oh,
1.
there's 3.
This is the first one. And oh, that's not the first one. Yes, 1. Okay.
Oh, it's only 2.
2. Yes, only 2.
It's 2.
2. All right. Yeah, 2 90s are there. Very good. All right. So now I can add these frequencies up to get the total count. It should be equal to total count, right? All right. What's the total? 6, 12, 18, 23, 27, 30. There are 30 altogether. Oh, I have no way of writing that here. All right, so let me write it here. 30 is the total. There's no room below that, so let's leave it there.
It's 29, I think.
Are you sure?
Yeah, 3 plus 4 plus 5 plus 5 plus 6 plus 4 plus 2 equals 29.
Okay, let me add again.
I put it in the calculator.
No, I'm coming about 30. I'm getting 30. 7, 12, 18, 24, 28, 30. Yep, I'm getting 30. Okay. Are you getting the same thing, Samantha?
Yeah, I keep getting 29.
Oh.
It could be my calculator's messed up maybe then.
7, 12, 18, 24, 28, 30. 30 is right. Okay, so let's go to the, so this is your frequency table right there, frequency distribution. Now, probability distribution has to be done next. We write Pi for the probability distribution part, P subscript I. That means probability of each value of the random variable. So what is the probability for the grade to be 40? If I select randomly, if I select a student randomly, what is the probability that the student's grade is 40?
3 over 30.
3 over 30. There are 3 students with 40 grade out of 30 students. So 3 over 30 is the probability. And as we discussed in the last class, probability is same as relative frequency. In other words, each frequency divided by total frequency. Total frequency is same as the total number of students in the class. So out of 30 students, 3 students have 40. So probability for 40 is 3 over 30. So it's same as frequency of that grade divided by total frequency. So 4 over 30 here and 5 over 30. Simply divide each frequency by the total frequency. 6 over 30. Do not reduce these numbers. When you're doing this for a histogram, it's easier if you keep them unreduced. 6 over 30 and 4 over 30. 2 over 30. Okay, so that's your probability distribution. So if they ask for the frequency distribution, it will be the second column. As for the probability distribution, that's your third column. And then it says, draw the histogram of the frequency of X. So that means on this graph paper here, you need to mark the frequencies on the y-axis instead of probability. If they ask for the probability histogram, then you have to put the probabilities. It's just the number that goes on the y-axis will be different, but the histogram will look the same either way. So I'm going to, I won't be able to do it here. So I'm going to go to the board and see if I can do it here. Okay. For the first one, I'm going to mark the probability or frequencies on the y-axis. So y-axis represents F. So you need to say F goes on the y-axis and the grades or values of the random variable goes on the x-axis. And the first one is 40. So I can mark the 40s here at this point and use the two squares before this 40 and after the 40 to represent the bar. So for 40, I have 3. So I can use, if I look at the numbers, frequencies go up to 6. So I can use 1, 2, 3, 4, 5, 6. So the first one is of height 3. So I draw the bar this way. See, the 40 is in the middle. That's normally how you like it. You can use 1 square if you like, but I'm using 2 square to expand it, covering wider range so that the picture will be big. If you don't want the picture to be too small. Next one is 50. So I mark the 50 here. And the frequency is 4. So here's the bar. And 55 is there. You don't have to have 55. And, in the graph paper, we normally have to have accurate representation of these numbers. But for the histogram, you don't have to. You're actually marking the data on the x-axis. And they don't have to be proportionately spaced. There are 2 squares from 40 to 50, doesn't mean 50 to 60 has to be 2 squares. We just have to mark those data here, that's all. So 55 has 5, so that's the bar for that. And 60 next, and we have 6. And 70 next, and I have 6 again. 75, no, 80, sorry, 80, you have 4. And 90 has 2. All right, so that's it, that's your histogram. Now, when you're doing it on the webdesign, you don't have to draw it by hand. It's going to be multiple choice, clearly. So now it says, how does it compare to the probability histogram? If I draw the histogram for the probability, how would that look? How would you compare that with this? It'll be same, right? Only difference is the numbers you put on the y-axis will be now, if it is probability histogram, this will be 1/30 and 2/30 and so on. And the histogram will be still same. Okay, find probability for x less than or equal to 55. Now, since we have the table here, we can easily find it by adding them. But if they give you just a histogram, can you answer that from histogram? Let's see how to do that from the histogram, because that's what you'll be doing in the homework. Probability for 55 is equal to the height of this bar, which is 5. The frequency is 5, or probability is 5/30. And so probability for the grade to be less than or equal to 55 will be the sum of heights of these 3 bars on the left of 50, less than or equal to 55. So the bar at 55 included. So the height of this bar plus height of the next bar on the left and the height of the other one. I had to add those. So that'll be 6 plus 4 plus 3, 10, 13. So 13/30 is the probability. Everybody see that probability x less than or equal to 55 is 13/30.
Professor, wouldn't we have added the fractions together?
Yes,
The probability?
the probabilities, yes.
So wouldn't we have added the fractions together?
Yes, that's what I'm doing. The fractions 1/30, 2/30, 3/30, 4/30 are the probabilities, right?
Yes.
So I'm adding those probabilities.
So adding 1/30, 2/30, and 3/30, you got 13/30?
Actually,
Oh, I'm sorry. Actually, never mind. Never mind. Sorry.
it actually goes to 55. 55 has a 5/30.
Yeah, so it would be 5/30 plus 4/30 plus 3/30.
Right. 5 plus 4, 9, 12 then. Yes. Sorry, I had it wrong. So it's 12/30. 5 plus 4, 9 plus 3, 12. Okay.
Yes, thank you.
Yeah, I had a 13 that was incorrect. So 12/30 is the probability. So you're adding the, if it is the frequency you have on the y-axis, you had to add up the frequencies and divide by 30. You know, you need probability means you have to divide by 30. Or if you have the probability numbers on the y-axis, simply add up those probabilities. It's the fractions that are probabilities that you need to add up. If you add up the frequencies, then you have to divide by 30 to get the probability. Okay, so that is the so that's the answer to the first question. And now it says shade the region that represents probability for x less than or equal to 55. That'll be these bars, right? You need to shade these bars, the 3 bars. Shade the region that represents x greater than 55. X greater than 55 will be the right side, which is starting from here, 60, these. I'm shading in the opposite way. Okay, so that'll be the probability for x greater than 55. So what would be the sum of those? What would be the sum of those?
1.
1.
Right. The entire probability will have to add up to 1. And if you add up these probabilities here in the table, these probabilities, they're going to add up to 1. That's clear. It's going to be 30/30 if you add them up. So all the probabilities have to add up to 1. All right, so that's just how that's how you do the histogram. We'll be visiting histogram again when we do a slightly different organization of the data. But now let's understand the expected value. Expected value of a random variable is the same as average value of all the values it takes. Basically same. But in statistics, we call that expected value because the average value is what you would expect when you don't know what the next value is. That's why it's called the expected value. The average is what we are trying to find, but we're going to derive a slightly different formula for it by using simple math here. So let's say to explain that formula, I'm going to use this example. There are 8 students in a class, and these are the grades of those 8 students. Then I need to find the average. So I'm going to average is the sum of those divided by the count, right? So it is the same idea, but we're going to derive a slightly different formula so that we can find the average or expected value, even if we don't know the count. Without knowing the count, if you only know the probability for each data, we want to be able to find the average or expected value using probabilities. So that's why we need to understand a new formula for the average, average or expected value. We are going to derive a new formula. So I'm organizing my data first to show you the frequencies and probabilities. So this same data I'm organizing, there is 68 with a frequency of 1. There is 79 with a frequency of 2. In other words, there are 2 students with a grade of 79. 84 is there 3 times. So that means there are 3 students with a grade of 84. 96 is there 2 times, means 2 students have 96 as grade. If I add up the frequencies, I'm getting 8, which is same as the class size. 8 students are there. And here's the probability distribution. It's 1/8, right? For this grade of 68, the probability, or in other words, if you select a random student, what is the probability the student has grade 68? It's 1/8. There's 1 is the frequency. You divide it by the total frequency. Similarly, 79 has 2/8, 84 has 3/8, and 2/8. These are the probabilities. Okay, now let's go to the formula of finding mean or average or expected value. These 3 names mean the same thing. It's also called mean. Okay, it's 68 is there 1 time, so 168, and 2 times 79, because there are 2 79s in there, plus 3 times 84, plus 2 times 96, should be added up and divided by 8. Okay, everybody agree with that, right? Instead of saying add up 84 plus, instead of saying add these up, it's the same as saying multiply 68 by 1, because there's only 168, multiply 79 by 2, there are 2 79s, so I'm multiplying by 2, multiply it by 3, and multiply this by 2, and then add them up. It's the same thing, right? That's why I wrote it this way. So this is the same as just adding them up and dividing by 8. But notice that I can split that fraction to write 68 times this 1, the frequency 1/8. In other words, this expression is same as this. Why is that true? It's a simple math. Let me go to the board. Let me show you on the board. You have learned in basic math that if you're adding 3/8 and 4/8, that'll be common denominator 8 and 3 plus 4 in the numerator. So I can go backwards and write this in the split form like this way. So that's what I'm doing. So let me do that on the board. 1 times 68 plus 2 times 79 plus 3 times 84 plus 2 times 96 over 8 can be split to write this over 8, which is same as 1/8 times 68, plus this over 8, which is 2/8 times 79, plus this 3/8 times 84, plus this over 8, which is 2/8 times 96. Now what's interesting here is 1/8 is the probability for the 68, for a randomly selected student to have grade 68. 2/8 is the probability for a random student to have grade 79. So what I have proved here is that each value each value of the random variable, which we call xi, can be multiplied by the probability for that value, and then you add them up. The sigma notation means, this is called the sigma, and if you open up a statistics book, you will see this symbol everywhere. And this is used to represent summation or add up. So when I write sigma, that means add up pi times xi, which means each value of the random variable should be multiplied by the probability for that value to occur and add them up. That's what this formula means. So we can say mean. Also, we can say expected value. We write it as E parentheses X, expected value of the random variable X, is same as one way to write that is sigma fi xi, which is what these are, frequencies times data, frequency times data, adding them up, and then divided by total frequency, which is same as sigma fi, adding up all the frequencies. That's what total frequency is. So we can write it as sigma fi. So if you open up a statistics book, first they will define expected value as this. Also, it's called mean. And then I proved that here using this example. I showed you that that expression is also equal to adding up probability times data. Each value of the random variable multiplied by probability and then adding up. In other words, this. So the same expected value has another formula, which is sigma pi xi. So this formula pi xi is commonly used whenever whenever you have only probability distribution available. You don't always have the original data available. In other words, you don't know the frequency data, you only have the probability data. If you only have probability data, you can still find the average or expected value using this formula. So just add up probability times data. So here is the conclusion. Expected value of X is given by sigma pi xi. Sometimes some books will use EV to mean expected value. What common notation is E parentheses, the name of the random variable X. That's a more common notation. Okay, so let's go to a simple example. In a test given to a class of size 10, for a class of size 10, a test was given. 4 students received 90, 3 students received 80, 2 students received 70, and 1 received 50. Then it says, if a student is randomly selected, what is the probability that he or she received 80? And then if a student takes this course next semester, what is the expected grade? And then what is the average grade? These are the questions. So the given information can be organized this way. The value of the random variable represents grade of the randomly selected student, clearly. So I'm listing those values. According to the problem, the grades are 90, 70, 90, 80, 70, and 50. So I have them in the first column. And there are 4 students with 90, 3 students with 80. So I have those frequencies. Those are the frequencies in the second column. Now, to find the expected value, I can multiply 90 by 4, 80 by 3. So summation of these divided by total size of class, which is 10. You can do it that way. Or, I mean, in statistics, when the data is already grouped into frequency distribution, like this table we have, frequency distribution, we prefer to do the work in the same table by extending the table and creating another column that's called FIXI. And basically, you're multiplying each value of the random variable by frequency. So That's part is 360, and 3 times 80, 240, 2 times 70, 140, 1 times 50 is there. Now, if you add up this column, that gives you the total of all the grades. It's just a easier way to add up. And if you just add it up, if you did this way, it's not wrong. But if you do it in a table, I mean, we are talking about very large number of data, a large table. It's much easier to do it in the table. So we extend the table to have another column and then do this calculation and then add them up, and it makes it easier. Now divide the 790 by 10. So that's your expected value, 79. All right, so the answer to the first question is, what is the probability that he'll received 80? 80, what is the probability? Can somebody answer the question? What is, if I randomly select a student, what is the probability that the student received 80?
Three out of 10.
3 over 10. There are 10 students and 3 students received 80, so 3 over 10. Second question, if a student is to take this course, what is the expected grade? Anybody?
79.
79. The expected value represents expected, exactly what it means, expected value. What would be expected if you took this course? What grade is expected? Same as the average. What is the average grade? It's the same thing. Expected value and average are same. So it is 79. All right, going to problem exercise 12. 100 raffle tickets were sold, and there will be one $300 prize. You understand raffle tickets. If 100 tickets are sold, not all of them are going to be winners. There will be one $300 prize, 2 $100 prizes, and 10 $2 prizes. Now the question is, what is the expected winning in this raffle? That means, expected winning means if you buy a ticket, what amount can you expect to win? That's same as the average value. So we need to figure out the average winning. Now you need to be careful. You need to account for all the possibilities. Very commonly, some possibilities are missed by students. And if you miss a possibility, then the whole thing will be wrong. So it would be best to organize the data in a table like we did in the previous problem. So that's what I'm going to do. Put on a table. The value of the random variable is the amount to be won. So X represents amount to be won. The winning amount. Okay, so Xi, the value of the random variable, goes in the first column, and the frequency goes in the second column. Or if they give you probabilities, then you have to put the probabilities. In this case, they've given us frequencies. So, okay, so there will be a $300 prize with what frequency?
1.
1. And $100 prize has what frequency?
2.
2. And $2 prize has
10.
10, right? Okay, now commonly students stop here and start doing the calculation. You have to be careful. How many have been accounted for? There are only 13 tickets accounted for, 10 plus 2 plus 1, but 100 tickets were sold. So we have to account for the remaining ones. What do you get for the remaining? What is the winning for the remaining tickets?
Would it be 100 subtracted by 13?
100 minus 13 is the frequency, yes. The so 70, 87. 87 frequency with what winning amount? What do I write here?
100.
No, you don't. You can win. There is one $300 prize and two $100 prize, and then 10 $2 prices. That's all the prices. The remaining tickets have no price, right? That's the idea of raffle ticket, right? So the 87 tickets have no winning, zero winning, and you have to account for that. The value will be 0 for 80 with the 87 frequency. So now we are ready to find the expected value. I advise that you do this by extending the column and finding FIXI. That'll be 300, 200, 2 times 100, 2 times 10 is 20, and 0. Add them up, 520, 520, and add up the frequencies, 100. Remember the frequency, because 100 travel ticket was sold, so the frequencies have to add up to 100. So the expected value is 520 over 100, which is 5.2. So this is what we call expected winning. So $5.20, that's your expected winning. So the expected winning is the price you're willing to pay for it. And so some problems will ask the question this way: what should be the price you should be willing to pay for this raffle ticket? $5.20. Because you know, you want to break even. So the expected value represents, so in other words, if you buy many of these raffle tickets, you expect to win $5.20. That's what it means. So that's what you can pay to break even. So therefore, to break even, how much should be the price of it? $5.20. Okay, let's do exercise 13. Again, it's supposed to be a problem for the students, so I will do the work with your assistance. In a lottery, one pays $5 and take a card from a 52 card deck. If the card is ace of hearts, you win $200. If it is any other ace, you win $10. Otherwise, you lose. What is the expected winning? Okay, so we make the two column to organize the work. And you're going to pay $5. We're going to put the winning amount here. So the winning amount is the value of the random variable. And that will be $200, but you had to pay to play this game, $5. So that means you had to account for the $5. So if you win 200, the net winning is 195, not 200, because you pay $5. Okay, so the winning of 195 will occur with, we cannot find frequency here, but we can find probability. So here's an example of probabilities. Okay, can somebody tell me the probability for winning the 200? First of all,
Will it be
18 out of 52.
1 over 52?
right, very good. There are 52 cards and you're allowed to select one card, and it has to be ace of hearts to be this winner of 200. So that means there's one element in the event, the winning event, and 52 elements in the sample space. So it's 1 over 52. Very good. That is correct. Now, the winning of $10, okay, $10 means $5 net winning. So I write 5 as the net winning with what probability?
3 out of 52?
3 out of 52. Very good. There are 4 aces, but one of them will make you the first prize winner. So the other three will make you the second prize winner. So going to the next one. If you get any other card, you win nothing, right? So therefore, the zero winning, what is the probability for that? It's the remaining probability. Remember, the total probability should be 1, right? So we have 4 over 52. If you subtract 4 over 52 from 1 minus 4 over 52, that's the probability for getting 0. So 48 over 52, 48, yeah. 48 over 52 is the remaining probability. That's what you have for the 0. Okay, so
Sir, do you mind if I ask, where did you get the number 4 for 0?
oh, there's 4. I added these probabilities. That's 4 over 52, right?
Yes.
I subtract that from 1 because we know that all the probabilities have to add up to 1, right?
I was just wondering how you got 4.
Okay.
Yeah.
I added 1 over 52 and 3 over 52, and then I am subtracting from 1 to get the remaining probability. That's 48 over 52. 1 minus 4 over 52 is the same as 52 over 52 minus 4 over 52. So common denominator 52 and 52 minus 4 in the numerator. That's how I got the 48. So there is 48 over 52 probability to get 0. Now, to find the expected value, we learned already the expected value equal to sum of PIXI, probability, each value multiplied by probability. So that's what I have to use now. So I need to find PIXI.
So since we have 4852 for 0 again, I'm sorry, would we be possible to put it in simplified form?
Yes, you can.
Okay.
But
I just wanted to know if we would leave it at that number or we would simplify it.
yeah, you can simplify, but there's no need to because it's not going to be calculated. It's not going to contribute to the calculation because this time 0 is 0. That's why I didn't bother to simplify that.
I was just wondering for like WebAssign.
The web assign would ask only for the final answer. They wouldn't care about what you write down in your work. Only the final answer matters.
Can you go over the expected value, please, Professor?
Go over the expected value in
For this
problem. Yes, that's what
yeah.
I'm doing.
Oh, okay.
So we are going to use the formula that expected value equal to sigma PIXI. In other words, each value multiplied by the probability that we proved in the previous section, previous page. That's what we had to use because in this case, we only have the probabilities available, not the frequencies. So I'm going to make a third column in which I'll show the product of probability and the XI value. So 1 over 52 times 195, that goes here. Let me do that on the calculator. 195 multiplied by 1 over 52 is same as dividing by 52. And that's 3.75. So that's 3.75. And then 3 over 52 times 5 is same as 15 over 52. 15 over 52 is 0.29. And this is 0. 48 over 52 times 0 is 0. So that's why I didn't bother to simplify that number. Now I need to add up these numbers, 3.75 and 0.29. And that gives you 4.04. So 4.04 is your expected value. I found the PIXIs and then I added them up. So this is the value of sigma PIXI, sum of products of probabilities and the values, 4.04. So our answer is 4.04. So your expected winning is $4.04. expected net winning. Okay. All right, everybody's clear? Any question on that? All right. We learned another expected value before. For expected value for a certain type equal to probability for that type times total count. For example, if the I have an example here. So this is something we did before. That's another expected value. So depending from the given data, you should be able to understand which expected value that you're finding. In Professor Smart's class, there are 20 students, 4 of them received A. So if a student is randomly selected, what is the probability that he or she received A? That's 4/20, right? 4 out of 20 students received A. Now, if the professor's next semester class has 20 students, how many are expected to receive A? Well, the probability for receiving A is going to remain same as long as it's the same professor. So 4/20 is the probability. 4/20 is the probability to receive A. And if there are next semester, if there are 20 students, then the number of students who are expected to receive A is going to be 4 again, isn't it? So
4 out of 10.
Same size class, so it's going to be 4 again. But we can also say it this way. The probability for receiving A in Professor Smart's class is 4/20. And so in any semester, if you want to find out how many students are expected to receive A, you can multiply the probability by the size of the class. That'll give you the number, 4. So if instead of 20 students, if there are 80 students, then you can do the same. Probability multiplied by total size, 20 divides 80 into 4, so there are 16. So if there are 80 in the class, 16 students are expected to receive A. That is another expected value we discussed before. And remember, based on the question and the information, you can see which one they are asking, which expected value. So if you have the size of the class and probability for getting A, then probability times total size will give you expected number of students. So even though they look like the different expected values, they're essentially same. They give you expected number. Okay, range of data. Now, if they give you long list of data, statistics is about analyzing list of data, a bunch of numbers given to you, you have to analyze. To analyze the data, you need to organize them, and frequency table, probability table, these are all ways of organizing the data. And we're going to learn more about organizing. And one of the things you need to understand is the range of data. The range means how far they go, the data. If the data goes like between 20 and 90, then we say 90 minus 20 is the range. So you subtract the largest data, smallest data from the largest, which is the difference between them is called the range of data. Now we will understand the grouping data into class intervals. Now in the earlier example, we only did, in the previous example over here, here in this example, we organized the data into a table showing all the grades in the first column and frequencies in the second column. Now this is possible only when the number of data is small. We are able to fit everything in this small table. If the number of data is very large, like 2,000, if you organize them this way, this table will extend to several pages. And that's not manageable. manageable data. So you need to bring it down to a manageable size data, something you can work with easily. So if the number of data is very large, organizing it this way is going to make it too long. The table is going to be too long. So therefore, what we do instead is we organize the table into intervals. Instead of saying grade 40 has frequency 3, now we're going to place intervals. 40 to 60 have so much frequency, 60 to 80 has this frequency, 80 to 90 has this frequency, so on and so on. So we group them into intervals. If the data is very large, the list of data is very large, to bring it down to manageable size, we organize them into what is called class intervals. So here is the data that I have a small collection to for the purpose of practicing, but this grouping is used when the data is very large list. We will use the grouping method to organize this data. So that means you had to come up with intervals, and when you are the statistician, so you decide what intervals are to be used, how big the interval should be, so that the table will come down to a manageable size. But when you're doing this as a homework problem or test problem, they will indicate how big your interval should be. So you can use whatever the problem tells you. So this problem says organize this data into groups of size 5. Part B says group this data into class size intervals of size 5. So you write intervals in the first column. 52 is your lowest number, as you can see. So you don't want to start your interval at 52. You want to start at 50. Some whole number is always the best idea. So you say 52. This interval is going to go from 52. Size is going to be 55. So if you write 55, it's not wrong. Some books actually write that. But the better way is to write 49.9 to mean that the numbers, all the numbers less than 55, I'm sorry, not 49 point. We're going 50 to 55, so 54 point. Sorry about that, it's 54.9. I'm writing 54.9 to mean that I'm going to count everything less than 55 in here. The 55 itself will be counted in the next one. That's why we don't want to write 55 here. But some books will write 55 here and then again begin with 55 here for the next interval, and then say 55 to 60. If they write 60, you still need to understand that the 60 is not going to be counted here. 55 to 59.9. That's a preferred way of writing to indicate that you're not counting, the 60 here. See, the point is, if you count 55 here, you shouldn't be counting 55 here. So as a rule, the right endpoint is never counted in that interval. So this one goes from 50 to under 55, everything under 55. So you cannot say what is the largest number under 55. So we write 54.9 to indicate that we are counting everything under 55. And then 55 will be counted in this interval all the way to under 60. And next one will be 62 what?
60 to 69.9.
64.9. The size of the interval is 5.
64, yes.
Yes, 64.9. And then next one will be, anyone?
65
to 69.9.
69.9, right. Okay, and we have numbers going all the way to 78. So I have to go from 70 to 78. 4.9, and then 75 to 79.9. I think that's where we need to stop because our numbers are limited to those. There are no numbers bigger than 80. And so now you count the frequency. The frequencies are going to be numbers in that range. How many numbers are there in this range? That's what you need to count. 52, 53.
I think 2 is for the first one.
Yeah, looks like we only have 2. Okay, 2. In the same way, you need to count them. I'm going to just make up numbers. We are running out of time. So let's say I have 4. I'm just making up 4, and then 6 numbers, and then 3, 2, 2. I just made up some numbers. And then you add them up to get the frequencies or count all the data to get the frequencies. Then the probability, I think the number of data here, I'll just use this number, 6 plus 4, 10, 12, 15, 19. Let's make this 3. So now it's 20. So 2 over 20 is the probability. So this means the probability for the data to fall in that range, 52, 54.9, 52, 55. This is probability for the data to fall in the range 55 to 60. That's what these probabilities are, 4 over 20 and so on. So these are identical to the probabilities just like before. So what's the difference? Only difference is now we have intervals. So if you have intervals, how do you do the histogram? The histogram is going to be slightly different. So let's see. Now we have intervals, so we do intervals. So the first interval 52, hold on. 52, 55. So here we can write 50 and 55, or sometimes some books will write 52, 55 right there, but I'm writing 50 for this end, 55 for this end, and the frequency 2, so 2 squares, so this is my bar for that. And then if I want a frequency on the y-axis, I can put the frequency. Or if they ask for probability, you put the probabilities. It doesn't matter. The histogram will be the same. And then 55 to 60, 4 over 20. So you have another bar. And so keep going, and you'll have the entire histogram. Now, everything else is just like before. What is the probability that let's answer these questions. Write the probability distribution. That's what I did in the last column. Probability distribution is what the last column is. Draw the histogram of the probabilities. So if it says probabilities, then that means on the y-axis you have to show the probability. Which interval has the highest probability? Here I have the interval 60 to 65 has the probability. So what's the conclusion from that? That means highest number of grades fall into the interval, if these are grades, or these are electric bills. The highest number of bills fall in the interval 60 to 65, and you'll be able to see that from the histogram. Which interval has the highest probability? 60 to 65. And what is probability for x less than 65? So you know how to do that. Probability for x less than 65 will be sum of these 3 probabilities. This is where 65 begins. So everything before, all the probabilities before that should be added up. So those are questions you know how to answer. So let's quickly do this one and then we'll be done. Exercise 14. Histogram is shown on the picture. Histogram for a certain group data is shown in the picture. Does this histogram represent valid distribution? What would you do to answer this question? Anybody? a valid distribution and normal distribution are two different things. Students sometimes mix them up when they answer questions. A distribution, probability distribution, is a valid one if the probabilities add up to 1. So the probabilities have to add up to 1. Now this histogram here, the probabilities individually are not given, but histogram is given. So using the histogram, you have to figure out the probabilities. Sorry. All right. So the heights of the bars represent probability. So you basically have to add up the height of all the bars. The probability for the data to fall into the interval 10 to 14 is the height of this bar, and it tells you each square represent 0.05. So 0.05 means it's 1.5. I'm sorry, 0.15. That's the height of this first bar. Second bar is 0.25. So add up all those heights. If they add up to 1, then that means the probabilities are adding up to 1. So therefore, it is valid. You want probability for data to, or random variable to be between 14 and 26. Then you have to add up the bars between 14 and 26. That'll give you the probability. Data in which interval has the highest probability? Which interval has the highest probability?
18 to 22.
18 to 22. And next question is this distribution normal? Is it?
Yeah.
Yes. As long as it has that pattern of going up and down, it's normal. It doesn't have to be symmetric. So that's how you answer those. All right. Now remember, it's a common error to, here's the wrong answer I get every time. In every test, I get this. Does this histogram represent valid distribution? And then I ask, justify your answer. The student says, yes, it is valid because it is bell-shaped. So you understand why it's wrong, right? He's answering normal distribution. That's what he's answering. So you need to say, yes, it is valid because the heights of the bars add up to 1. The probabilities add up to 1. That's why it's valid. And then if it says, is it normal, and justify why, then you say, yes, normal, because the graph, the histogram is bell-shaped. All right, that's how you answer that. All right, so we'll quit here. And oh, I thought we can get to the next worksheet, but we didn't. But these are just additional exercise problems. We don't need to do them. So we're done.